So the water filling, or also known as water pouring algorithm, is a name given to a very known idea in wireless communications or communications in general. It is a design mechanism or algorithm to allocate power, let's say, in a smart way. So as the name suggests, or even pour water or power in certain channels in a smart way. Now we'll see how. So let's say I've got a base station right here that should transmit to some users. Okay, so this is what I've got. The 5 boxes or squares that you see are users. So we've got 5 users in this simple example and a base station. So the base station happens to know the channel gain between each user and itself. So let the channel gains be denoted as HK. So HK denotes the channel gain between user K and the base station. So H1 is the channel gain from user 1 towards the base station, and so on. Furthermore, let's say that the noise at each user is denoted by sigma K. So the noise in the equipment at user 1 is sigma 1. That's the standard deviation of the noise. The noise at user 2 is sigma 2. That's the standard deviation of the noise random variable, and so on. So an important ratio here is the channel gain to noise ratio, the CNR. Okay, so we're going to denote the CNR simply by C. So CK would be the magnitude HK by sigma K square, right? Now, why is this ratio important? It's because you can express the so-called capacity or rate between user K and the base station through CK. And what is it? It's the following. So let's say you want to know, let's focus on user 1, and the base station right now wants to respond to user 1. So H1 would actually give an idea for the base station on what is the capacity of the channel. It tells you the maximum bits you can pump in channel 1. And this is given by the following. So log 1 plus pk ck. Okay? Ck is already defined. It is the magnitude of h k over sigma k squared, the channel to noise ratio, and pk is the power in which the base station, the power of the signal that the base station would want to transmit to user 1. Okay? So pk is the power. And water filling will actually, given the ck's, would compute how much pk's I need to maximize the data rate of the system. So in other words, we're going to maximize the sum k going from 1 till n. Let's say we've got n users. So n is the number of users. And hence, the sum will give me the total capacity of the system. So my goal here, or my objective, would be to maximize this term, right? So let's formulate a possible rate maximization problem. So we'd want to maximize, we'd want to maximize the total capacity of the system. So if we leave the problem as is, and given that we're maximizing with respect to P1 down to Pn, then the solution is trivial. Since log is an increasing function, then all your pKs would be infinity. So just throw in infinite power in each channel. But This doesn't reflect reality, and hence the following problem is not interesting. In real life scenarios, we got some constraints, right? So the first constraint that could pop up in anyone's head would be, we can't allocate negative power, right? Because power is always positive. So all your pKs should be positive, right? And also, in real life scenarios, you always have a power budget. So you're always restricted to transmitting no more than a certain total power. So the total power, that is the sum of pKs, should be equal or less than, we're going to set it equal to the total power, PT. This is the total power budget that you have. Now, in some references, you will find instead of this equal, a less than or equal, right? But keep in mind that the more power you pump in, the higher capacity you achieve, right? So this inequality is usually replaced by an equality, right? So how do we solve this problem? Well, first of all, this problem is convex. Why? You're maximizing a concave function in p's, right? P1 down to Pn, subject to affine constraints, right? So those two constraints are linear, hence convex. Now one might say, oh, but we're maximizing a concave function. Isn't this a concave optimization problem? Well, maximizing a concave function is the equivalent of minimizing a convex function, right? All you have to do is just insert a minus right here. Minus log is convex, and the maximization is now a minimization. So we're going to leave it as is, and we're going to formulate the Lagrangian function. That is a function in all my powers, P1 down to Pn, and the Lagrangian multiplier. So we've got lambda we've got n lambdas, that is lambda 1 down to lambda n, where lambda k is associated with pk positive, and we've got a mu associated with the equality constraint, right? So the Lagrangian function would look like this. So it's the objective function, that is the total capacity, minus the sum of the Lagrangian multiplied by pk. So those are the terms taking into account the positivity constraint, pk positive or non-negative, and the equality constraint, so minus mu, sum of total powers minus total power, pt. Okay? Now, this is the primal problem. The problem we have in hand is the primal problem, and we'll be interested in formulating the dual problem. So the dual would be to, since we've got a max, it will be to minimize the Lagrangian dual function, which we didn't write down yet. We're going to derive it just now, which will be a function in only the Lagrangian multipliers, and it's denoted by g, subject to positivity constraints on the lambdas. So the lambda k's are positive. Now, what is the Lagrangian dual function g? So g would be the supremum over the p's on the Lagrangian function, right? So the way to maximize or to find the supremum is to derive with respect to each and every one of those p's, right? So let's find the derivative of the Lagrangian function with respect to pk, right? So deriving L with respect to pk, we've got a sum of logs. So we know that the derivative of log is the derivative of the argument over the argument itself. So deriving with respect to pk, pk only shows once in the sum log, right? It shows in the kth term, log 1 plus pk ck. So the derivative would be ck over 1 plus pk ck, right? Now in the second term, again, pk shows once and lambda k pk, so the derivative would be a lambda k And last but not least, in the final term, we've got a mu, we've got pk showing once in the kth term of the sum, and hence we'll be left with a mu. Okay? Now setting this to 0, we're going to solve for pk. So we're going to get the following, which is equivalent to getting the 1 on the right hand side. We'll get ck. Now divide by ck on both sides, and this is what you get. So the pk is 1 over lambda k plus mu minus 1 over ck. Now, one important thing to note here is that since pk's are positive, then this term should be positive. And hence, while choosing the Lagrangian multipliers, this thing should remain positive. So this will be taken in the positive sense. So if this thing is negative, we set it to 0. So this superscript plus means, so x plus means the max of x and 0, right? So now since, pk's are all positive, then we can go back up here and just do a small modification on the Lagrangian function. So since we guaranteed that our pk's are positive, thanks to this plus over here, then we can just choose lambda k's to be anything that is positive. So without loss of generality, we're going to choose all the lambda k's to be just a lambda. Okay? So we're going to choose it to be just something, we're going to choose that set. We're going to choose all the lambda k's to be the same, right? Actually, we can just set all our lambda k's to 0. Since we guaranteed the pk's to be positive, then I could just, set all my lambda k's to 0. Because I don't care anymore about this constraint right here, the positivity constraint. Why? Because we just, forced pk's to be positive. So no matter what lambda k's you're going to choose that are positive or 0, this is always guaranteed to be positive. So it's as if we don't need this constraint anymore. So I'm just going to, set all the lambda k's to 0. So this term right here is gone. And hence the lambda k's are 0. So my pk could be written as 1 over mu minus 1 over ck plus. Okay? So this is my pk star, the optimal power. And I'm going to plug it in the Lagrangian function to get the Lagrangian dual function. So my g mu now, we don't have lambdas, is just L p1 star down to pn star and the mu. That is the sum of 1 plus pk star ck minus mu, sum of pk minus pt, sum of pk star minus pt. Now plugging the expression of pk stars and what we have, we get the following. So the following is just a function in mu. So now all we have to do is minimize the Lagrangian dual g of mu with, of course, with respect to mu, to find mu. And once we get mu from this minimization, from this 1D minimization, so it's just a 1D function through mu, we denote the optimal solution by mu star. You get mu star, and then you compute pk star by just plugging in mu star. So all your pk stars would be 1 over mu star minus 1 over ck plus. Okay? So this is the solution to to the problem. Now, to appreciate the water filling algorithm, it's really interesting to look at the interpretation of the Lagrangian multiplier mu. Now, what does 1 over mu reflect? Of course, 1 over mu and 1 over ck are interpreted as powers, right? You can't just subtract two quantities, give power, unless each quantity is a power itself. Now, 1 over mu is the power level in which you will not exceed this limit. It's a limit. It's a power limit in which you will not exceed it in each and every channel. So if we've got 5 users, 1, 2, and we're allocating power to each and every user, then 1 over mu star, say it's over here, is the maximum power you can allocate for any user. You could allocate less, but not more, right? Why not more? This is mathematically obvious because 1 over mu minus a positive quantity is always less than that quantity, right? So that's how you can see it. And once you have the 1 over mu star, you can simply, and the CKs of course, you have this knowledge, you can just compute the PKs. So P1 star could be over here, P2 star, 3, 4, and let's say user 5 to the maximum. Okay? Now, another important interpretation is the following. So imagine the case where CK is 0. What does CK0 mean? We're taking one extreme case. It means the channel towards user K is in a deep fade mode or in a deep fade situation. The channel towards user K is very bad, right? So if this channel is very bad, 1 over 0 pops up to infinity, and hence any mu star that you choose that is finite will not yield this quantity to be positive. It's always negative. And hence, the max between this negative quantity and 0 is 0. So you will allocate 0 power to a channel that is bad. On the other hand, if CK is infinity, so 1 over infinity is 0, right? You will allocate maximum power, that is 1 over mu star. So you cannot allocate more than 1 over mu star. We already said that. So those are the two extreme cases. You either don't allocate anything, 0 power, when the channel is bad, and when it's extremely good, you just give it maximum power. So yeah, this is the water filling algorithm. This is how it works. Now, of course, indeed, there's a lot of literature on water filling, and in particular when, this mu star, you want to calculate it. So as you can see here, this function is really nasty. To compute it in practice, imagine you'd have to do a binary search or a 1D search over mu to find the best mu that minimizes this cost. This is not a smooth function. It's not differentiable. It's due to the max function, the plus, the superscript pluses. Many researchers have done a lot of work on how to compute this mu in an efficient manner, or how to reformulate the water filling problem or the rate maximization problem in a way to avoid this nonlinear search. Note that the nonlinear search is optimal, but is computationally exhaustive. You're searching the optimal mu of a nonlinear, which is a variable of a nonlinear function. Okay. Right now, we're going to write a MATLAB code that receives the CKs, the channel to noise ratio, or the CSIs, the channel state information, and based on the CSIs and the total power budget, the PT, we're going to compute the PK stars through this minimization, this nonlinear minimization, and this PK star equation. Okay? So I've got a script called water filling, open, an empty script on MATLAB. So I'll create a function called water filling, in which I'll pass it some CSI information, so the vector of CKs, and a P total. Okay? Now, CSI will be a vector of size, let's say 1 by n, right? And P total is a positive quantity. Okay, so now let's extract the length of CSI first of all. And without having to write a loop to, first thing we want to do is compute mu star, right? So we're going to have to compute this function, then find its minimum. What mu minimizes this function? Without having to write a loop, because MATLAB is so slow when you write a loop and so fast when you do smart matrix computation, matrix vector computation, so we're going to do the latter. That said, let me create a mu axis, which is positive. So it starts from a very small number, so let's say 10 to the power minus 15, ends, let's say, at 5, and has m points. M is a user-specified precision. It's the number of grid points you'd want to compute the Lagrangian dual, g of mu. So my pn's are given in this equation, that is 1 over mu axis minus 1 over CSI. Don't forget the transpose right here so that we do a n by m matrix. And we're going to take the maximum of this guy and 0. This is the plus superscript. Okay? Next, we're going to compute the Lagrangian dual function given here. So I'm going to replace pn's that are those quantities right here. So we've got a sum of logs of 1 plus pn times cn. Now cn, or the CSI, is not trivial, but let's do this. 1 by m. So this is the first term minus mu times the sum of pn minus p total. Okay? Next, we're going to have to find the minimum of g. So we're going to find g that is equal to min g. And we need the index of this guy. So min g is the first element and the index is the second element. Why do we need the index? To compute the optimal mu. That is the one sitting at the index. In mu axis, of course. Now over here, let's do something before we continue. Right now, we're going to open a figure and plot the mu axis with respect to g. Okay? Take some grids and let me just print the mu. So I'm going to display mu. So over in the command window, let's generate a random CSI. So say I've got 5 users. This is my CSI. And P total is 10. It's called water filling. Pass it CSI and P total. So look what we have here. This is how the G looks like. As we can see, right here, the minimum happens at 0.234. So somewhere around here, right? This is the best mu. Of course, the one that minimizes my G, right? Let's give it an X label. That is my mu. and a y label. That is my g of mu. So run. There you have it. This is the mu, and this is the g of mu. So this guy is the best mu. Let me comment this off because we don't need it. Let me remove this. Let's continue with the flow. So we got the best mu. All I have to do right now is compute the optimal powers. So it's max 1 over mu minus 1 over CSI, and that's it. Okay? So let's open a figure. And on this figure, I'm going to put two subplots. The first one telling us the power allocated to each user, and the second one just a plot of the CSIs, right? So that we see the higher the CSI, the more power we get. The lower the CSI, the less power we get. So two subplots where in the first subplot I'm going to have the following color. So this, and a bar plot would be best here. And on the second subplot, we'll plot the CSI as such. So let's run it again. Oops, this is too bright. It's too bright. Let's just set it to white. And there we have it. Just give this a red color. And this guy, there you go, red and blue. Now let's give some information right here. Give an X label, users, and a Y label, power allocated. Same thing to the second subplot, users and CSI. Let's give a title to this whole thing. Water filling algorithm. Okay, good. Looks good to me. And let's make a more useful title. Let's show the total power that we actually consumed. Total power is the sum of my optimal powers, right? So it might not be exactly, in our case, PT. It is 9.99. Notice that the total power that is inputted to the water filling, the total budget that we have is 10, right? However, we use 9.99. Well, not bad. And one other thing is to plot on the first subplot a horizontal line representing maximum power level, that is 1 over mu star. So in the first subplot, I'm going to hold on and then plot. Well, before that, let's get the x limits and then plot x lim 1 over mu to 1 over mu because it's horizontal, and in a dashed black line, right? So run, and there you see the maximum power level, right? Okay, so this is it. This is the water filling method. Let's see what happens on a small example. So I'm going to run the water filling on the following. So imagine I have a CSI vector, following values. So 10, 1, 0.1, 0.01. So 4 users with a total power of 30. Now, as you can see, the better the channel is, the more power I allocate to this channel. Now, as the CSI decreases, we can see that the power that should be allocated to a bad channel should be lower. In the extreme case where the channel is really bad, we allocate no power whatsoever. Now, to see this better, I'm going to run the method over multiple scenarios. So as we see right here, we've got a total power of 350 users. You see some channels fading away, right? And the corresponding power to be allocated to those channels decrease, right? Whereas more power is being allocated towards better channels. There is, you can see as the channels are getting better and better, we allocate more power, right? Here there's a fade in channels corresponding to users 40, 41, 42, and hence they get less power, right? So yeah, this is how you can visualize the water filling algorithm. So this is it. This one we talked about the water filling problem and the algorithm that solves this problem when applied to communication systems. So when applied to the rate maximization problem under power constraints, we formulated the primal and the dual problems, solved the problem through the dual. That is, we computed the Lagrangian multiplier that enables us to compute in closed form the powers for each user. We also showed how to implement this on MATLAB and gave some interesting examples. This is it for this one. I hope you enjoyed it. If you found this video beneficial, please consider subscribing to the channel and leaving a like on the video. If you have any question whatsoever, just leave a comment down in the comment section below and I'll get to you as soon as possible. Thank you so much. Happy water filling, and I'll see you then.